All right, let's start. All right. Everybody have a good weekend. Get a lot of sleep. I slept a lot, so that's pretty great. All right, well, it's a bright new Monday, so let's begin. So today we're talking about Extrema on an interval. That sounds exciting. So a few announcements. We've got homework due tonight, 11:59 p.m. Make sure you get it done. It's a little bit of related rates and a little bit of other stuff. Okay, so there's also new homework assignment in Canvas due next Monday. That one is mostly what we're learning today and later in the week. Okay, so make sure you get that done. And if you have any questions about anything, my office hours are 1 to 3 today, and also 1 to 3 on Wednesday and Friday. You can always show up in person or use the Zoom room. Okay, so any questions on these announcements? All pretty standard. Okay, so I want to finish up related rates with one more problem. Okay, so last time I wanted to cover this, but I didn't. So we're going to cover it today. So a rocket is launched so that it rises vertically. The camera is positioned 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time so that it stays focused on the rocket. Okay. So always start these problems with a drawing. So what should I draw first? It's Monday. Yes, let's draw a rocket. I'm launching the rocket, so let's draw it. Okay, so here we go. Here's the ground from which the rocket is launching, and then it's, here's the rocket, and we got flames shooting out. Okay, that looks great. All right, and so the distance it rises is changing with time, right? So I should label this distance with a variable. I'm going to call it y because it's launching vertically. Okay, you can call it whatever you want, but I'm going to call mine y. Okay, and then we've also got, what else is in this setup? What else is in this problem that we should draw? Yeah, I should draw this camera that's, what, 5,000 feet away? So here's a camera. And it's watching this rocket, okay? So this camera, is this distance changing at all? How far away the camera is from the launch pad? Correct, it's a constant. Thank you, Saba. It's a constant. So I should label that with a constant, okay? If you did not see that in the problem, it does not hurt to label it with a variable, okay? But if anything's not changing with time, if you're certain that anything in a related rates problem is not changing with time, I would, in the drawing, label it with the constant value that you know that it is, okay? What else should I label? There's really one more thing I should label on here. What's the thing that I'm interested in? I'll go ahead and label that H because that's also changing with time. But is that what we care about in this problem?
The angle of camera?
Yeah, I need the angle of the camera. I'm moving this camera up and down. I care about that angle that it makes with the ground here. I'm going to call that angle theta. Okay. So as to not confuse people, I'm going to erase this H because we don't need it at all. And that is definitely part of the art of related rates problems is recognizing what you do and do not need. Okay. So I care about, well, what am I given? First of all, I'm given what? I know camera's position 5,000 feet away. That's given. I already labeled that in my drawing. What else am I given?
That the rocket is 1,000 feet above the launch pad.
Yes, and what else about the rocket in particular?
Its velocity is 600 feet.
Yeah, the speed, right? So the velocity of the rocket is 600 feet per second. How do I write that mathematically?
The dv dt equals 600 feet per second.
Yes, very good. So I'm using y here, right? So I'm going to do dy dt is equal to positive 600. This distance that it's traveling vertically is growing. So we want a positive 600 feet per second. Okay. And then I'm going to incorporate the 1,000 feet actually in the want to find. Want to find. What do we want to find?
d theta dt.
Yes, we want to know how fast do I need to change this camera angle so that I keep the rocket in focus. Well, that's how fast does that angle change? That's just d theta dt. Okay, change in theta with time, specifically when y is equal to 1,000, when the rocket is 1,000 feet above the ground. Okay, cool. So this is rising vertically, so that's a right angle, by the way. Okay, so I've got all of my givens. I've got all of my want to finds. Someone asks why dy dt instead of dv dt, because I labeled my vertical distance y. There's no v's in my drawing, so I wouldn't label anything dv dt. Okay. So I've got my givens. I know what I want to find. What am I missing for a related rates problem? Hint, it's in the name. I've got my rates. Yeah, I'm missing the related part, right? I'm missing how are theta and y. Y is what I know about. Theta is what I don't know about. How are they related, right? So how are theta and y related here? Well, this is a triangle, so remember, and I mean, we've got a triangle and we're interested in an angle now. So it's going to be trig. So remember, so, ka, toa. Okay, I would use that to guide your answer. I would not use sine here, actually.
Tangent?
I would use tangent because we have the adjacent angle to, or sorry, the adjacent side to theta, which is 5,000, and we're interested in the opposite side, which is y. So the relationship is going to be TOA. Tangent is opposite over adjacent. Okay. So then, TOA, tangent of theta is equal to, well, it's equal to opposite y over adjacent, 5,000. Sehr gut. All right, and with that, we're ready, because now that we have our relation, what do? Well, I want to get a d theta dt out of this, right? So how can I get a d theta dt out of this?
Apply the derivative.
Yes, I'm going exactly right. I'm going to apply the derivative with respect to t on both sides. That's exactly right. So I'm gonna, when I do that on the left, I'm gonna get d dt of tangent of theta equals, when I do that on the right, d dt of y over 5,000. Very good. All right, we'll do the right-hand side first. That's a little easier. So what do I get on the right-hand side when I take the derivative with respect to t of y over 5,000? Have it in the chat. Right-hand side, what's the derivative with respect to t of y over 5,000? Well, this over 5,000, that's 1 over 5,000. That's just the constant. So if anyone's thinking you need to use the quotient rule, no, it's way easier. This 1 over 5,000 just pulls out in front, and then I just need the derivative of y with respect to t. But that's just, we just write that down. That's just dy dt, right? We know what it is. We're going to plug that in a second. But that's all we can really write there, right? Okay, so the left-hand side, the derivative of tangent of theta with respect to t. Well, does anyone remember the derivative of tangent? Yes, we could. Yes, if you forget the derivative of tangent of theta, you can write it as d dt of sine of theta over cosine of theta and work it out from there. But we actually have already done this. So I'll jog your memory. The derivative of tangent of theta is actually, with respect to theta, is secant squared theta. And then what do I need to, am I done? This is the derivative with respect to theta of tangent of theta. I wanted a derivative with respect to t of tangent of theta. So what do I need to multiply this by? Perfect, d theta dt. And that just follows from the chain rule, implicit differentiation, whatever you want to call it. It's ultimately all the chain rule, but. Okay, and then secant squared theta, that's the same thing as 1 over cosine squared theta. So if I divide by secant squared theta, that's the same thing as multiplying by cosine squared theta. So if I want to get this secant squared theta on the other side, divided by secant squared theta. Well, this is actually the same thing as d theta dt equals cosine squared theta over 5,000 dy dt. Okay. All right, and we're almost there. So dy dt, I know. Cosine squared theta, yeah, question. So secant squared theta is, I'll write this out right here. This is 1 over 5,000 times dy dt divided by secant squared theta is 1 over cosine squared theta. So I just flipped and multiplied. Flip the bottom.
Professor Matheson,
Yeah.
why didn't we get rid of the 5,000 since it's a constant? Is it just because there was a y over top and you couldn't get rid of the fraction?
Yeah, so when you're multiplying by a constant, that constant just comes along for the ride when you take the derivative. So you can think of it as, if you want, you could write out like the product rule, or you could write out the quotient rule with this. You'd end up with the fact that that 1 over 5,000 just stays put because it's being multiplied by the function.
Thank you.
Yep. Any other questions? Is secant squared theta given on the exam for the derivative of tangent of theta? Let me think about it. I'm going to think about that. I'm going to say I don't want to commit to anything yet, but we'll see. Okay, so before moving on, I know dy dt, right? We know that's 600. So this is going to be, at the moment we care about, this is, I don't know, well, in theory, I don't know theta, but I know dy dt is 600. So how could I find cosine squared theta? That's just cosine of theta, and then you square it, right? How can I find cosine of theta?
You can plug in your 1,000 for y and then use the Pythagorean theorem to figure out the hypotenuse.
Exactly. So I'm going to actually redraw my drawing a little bit at the moment we care about. So at the moment we care about, the rocket is 1,000 feet in the air. The camera is still 5,000 feet away. We want to find theta. Well, to find cosine of theta is really what we want to find. I need to know the length of the hypotenuse, okay? So mixing the hypotenuse at the beginning actually wasn't a bad idea. We do need to know it, but it's not related to how anything's changing. So that's why I didn't want to label it. Okay, so the length of this guy, yes, we use the Pythagorean theorem. So that's going to be the square root of 1,000 squared plus 5,000 squared. Okay. I'm just going to leave that like that for now, for time. Okay. So then cosine of theta, well, remember, SOHCAHTOA. Cosine of theta is adjacent over hypotenuse. Okay, so cosine of theta is 5,000 over the square root of 1,000 squared plus 5,000 squared. Okay. Any questions there? On an exam, you'd get a calculator for this problem, by the way. So then I can plug in everything I know, because now I know cosine of theta. So that means that cosine squared theta is just 5,000 squared over the square. We'll cancel the square root in the bottom, 5,000 squared over 1,000 squared plus 5,000 squared. Okay, and so we're going to be left with d theta dt, when I plug this in, is equal to 5,000 squared divided by 1,000 squared plus 5,000 squared. So there's cosine of theta times, and then to help with simplification, I'm going to move this 5,000 under this 600 just to help you guys see what's happening. So this is cosine squared theta times 600 over 5,000. And the only reason I did that is so that I'm not dividing this guy all by 5,000. It's so I'm multiplying by, oops, so that I'm multiplying by 600 divided by 5,000. And then magically, we get a little bit of cancellation there, right? So then we get d theta dt. is equal to 5,000 times 600. Well, that's 30, and then 5 zeros, 1, 2, 3, 4, 5, divided by 1,000 squared plus 5,000 squared. If anyone wants to type that into a calculator, you can be my guest, but you don't have to. Okay, do we have any questions on this? Chat. We're not interested in a fixed angle because, let's see. Yes, that's, oh, excellent question. Yeah, we're not interested. I didn't find that theta before because theta is changing with time. So I didn't want to label that in my drawing to start. Only after I've taken derivatives and want to plug everything in, only then do I want to find out specifically what theta is. Okay? Yeah, excellent question. Any other questions? I'll plug that into a calculator and write that in after class. Okay. All right, so this genuinely is the hardest related rate problem I would ever consider giving you. Probably not even on an exam. It's a little long for an exam. Okay, so so you know, this is the hardest related rates problem you'll probably see this semester. Okay. But at its heart, it's still just what we did before. Label your drawing, find your relation, take a derivative, plug everything in that you know. Okay, that's all it is. Okay. All right. So with that, we're going to move on to our next topic, which is extreme values. Okay. So as humans, and really just as living things, we're interested in extreme values. Okay, so we care about how high I can throw a ball. What's the highest point that that ball goes if I throw it into the air? What is the minimum cost that I have to pay to keep my business running? Okay, how do we maximize our grades? I want to get 150%, right? So calculus is the perfect tool to answer all of these questions. Specifically, the derivative. Okay, so we're going to look at a few examples of why this is the case, why the derivative plays such an important role in finding where is the maximum of the path that the ball takes, or where is the minimum cost that I need to pay. Okay, so, but first we're going to define a few things. So f is going to be a function defined on an interval I. So typically this is going to be either, typically this is going to be either the closed interval a to b, where a and b are real numbers, or the open interval a to b, where again a and b are real numbers. Typically, you can have other, I mean, there are other intervals. There are half open intervals. You could have like a to b like this, or a to b like that. We're not usually going to look at those, though it's not out of the realm of possibility. But for today, we're looking at either that closed interval or the open interval from A to B. Okay. And also, we're going to say that C is a number in this interval. Okay. Then f of C is a minimum of f on I if, well, it's a minimum, so it has to be smaller than everything else, right? I mean, English should match up with our understanding of math. So if f of C is less than or equal to f of x for all x, for all x in the interval I. Okay. So all this is saying, this is mathematically saying that f of C is the smallest that f could possibly be. Okay. Now, f of C is a maximum of f on I if, what's going to change in that line above? what would it mean intuitively for f of c to be a maximum?
Greater than or equal to f of x.
Exactly. The only thing that's going to change is if f of c is greater than or equal to f of x for all x in the interval I. Okay. So the minimum and maximum of a function on an interval are called the extreme values. Okay. Extreme values. Or if you don't want to say extreme values, people also say extrema or extrema. Okay. So the minimum and maximum of a function on an interval are also called the absolute maximum, or I said minimum first, sorry, the absolute, and I'll usually say absolute min, so I don't have to say so many syllables, I'm lazy, and absolute max. So if I say absolute min or absolute max, I mean the extreme values of this function on this interval. Okay. Oh, gotcha. Okay. Questions? So it's all pretty intuitive what if I say absolute maximum of a function, what that should mean. Extreme values, maybe not as much, but now you know I just mean either the maximum or the minimum. Extreme value just means one or the other, okay, or both. But that's the definition of extrema. Okay, so these extreme values, if we're looking at an interval, they can occur either at points inside of the interval or at the endpoints. Okay, so here's an example where both the extreme values occur at the endpoints of an interval. I have this function f of x is x squared plus 2x plus 1, and it has extrema, so absolute maximum and absolute minimum at the endpoints of I. And when that happens, I'm almost never going to say this, but when that happens, those are called endpoint extrema. So here's a graph of this function, okay? So we can see it has an absolute minimum at -1, and the minimum value is 0. Okay? It has an absolute maximum at x equals 2, and a maximum value of 9. Okay, so this is finding where the absolute minimum and absolute maximum occur are going to be very important for us, but actually finding the values, the absolute maximum and absolute minimum values, is also going to be important. Okay, so this again we would say has an absolute maximum at x equals 2, the maximum value is, I believe it's 9, right? Yeah. Okay. So making the distinction between where this absolute maximum occurs and what the value actually is important. Okay. So that's exterior, or sorry, the endpoints. But the extreme values can also occur on the interior of the interval. So here's an example where the extreme values both occur inside of the interval, not at the endpoints, okay? So here we've got this function, it's sine of x divided by x, where I define f of 0 to be 1. Okay? And when you do that, it magically makes this a differentiable function, which we can show for ourselves. But when you do that, then this function has an absolute maximum at, well, I'll write out at instead of that, at x equals 0, right, which is an interior point. The interval that I'm looking at is -1/2 to 2 pi, closed interval, okay? Absolute maximum at x equals 0, and the maximum value is 1, okay? This has an absolute minimum at about, let me write x equals, at x is about 4.5 with a minimum value, of about minus 0.2. Okay. It's even possible for a function to have 2 or more absolute maximums. So just think of just sine of x on any interval that's oscillating. It oscillates to plus and minus 1 over and over and over again. So if you take any interval where it hits +1 multiple times, we would call both of those absolute maximums. Okay. So a function does not have to have an absolute maximum or minimum on an interval, though. So for instance, if I is the open interval from 0 to 1 with the function f of x is 1 plus x squared, then f of x has no extreme values. And I know someone's going to push back. I know most of you want to push back, and that's okay. That's all right. So I claim that this function that we're looking at here has no extreme values. Okay? And it's because we're looking at it on an open interval. So let's say that last function was sine of x over x. Let's say we're looking at this function, and let's say that you tell me that, well, clearly this has an absolute maximum, absolute max at x equals 1. Okay, but x equals 1 is not in the interval we're looking at, because this is the open interval from 0 to 1. And what that means is this is all the x, 0 less than x less than 1, strictly less than. So 1 is not in the interval here, okay? So then you might say, well, what about x equals 0.99? Well, f of x, f of 0.999 is bigger than that, okay? And then you say, well, what about that? And I say, well, then f of 0.9999 is bigger than that, okay? So if you keep playing this game, your only possible choice for the point where this has an absolute maximum is 0.9999999 repeating over and over again. But, and this is, if you want to be a math major, you'll be able to prove this. 0.9 repeating is actually equal to 1, okay? So, and 1 is not in the interval. So this has no absolute maximum. And by the same reasoning, it has no absolute minimum because 0 is not in the interval. Okay. Everyone should be math majors. So what was special about these last two examples over the third one? Well, who can tell me maybe? The issue doesn't seem to be the function, because this function is shifted around, but it looks almost exactly like this function, right? This function had absolute maximums and minimums. This function did not. So it doesn't seem to be an issue with the function. It seems to be an issue with what?
This one's an open interval.
Yeah, it's the interval, exactly. It's a problem with the interval. This one has an open interval. These guys both have closed intervals, and that's not by mistake. Okay, that's a very important thing. So this brings us to the extreme value theorem. There's something very special about closed intervals. And the fact that this is a closed interval tells us if, and this, we're not going to prove this theorem. It's actually very difficult to prove. If you're a math major later in your career, you'll prove it. This theorem is called the extreme value theorem. If f of x is a continuous function on a closed interval, a to b, then f has both a minimum and a maximum on that interval. Okay? This is called the extreme value theorem. It only requires f to be continuous. F does not need to be differentiable, only continuous. I had a question in the chat. Was the function sin of x over x? Yeah, in that last example, you could think of the limit there exists, but the function isn't defined at x equals 0 or 1. Yeah. Okay. So this theorem here guarantees us, under the right conditions, that it's not a futile search to try and find these maximum and minimum values. Okay. And it's a pretty relaxed theorem, really. You only need continuity and a closed interval. So how does this help us? Well, we need to know where to look for these extreme values once they're guaranteed to exist by this theorem. Okay, so this theorem guarantees the existence of our extreme values. So once we know that the extreme values exist, there's only a handful of options where they can exist. Okay. So coming back here to look at these two examples, specifically this one, what's special about the two extreme values here? And think about the derivative. And if anyone's taken the class before, don't answer yet. Yeah, let's give people who haven't seen it yet a chance to try and guess. What's special about those 2 points? Oh. Yeah, exactly. The slope there is 0. It's got a horizontal tangent line, right? So that's a very important fact when we're trying to find these maximum and minimum values. There's only going to, the handful of places to look are going to be places where the function has a horizontal tangent line or at the endpoints. Those are really the only options, okay? So let's talk about relative extrema before we move on, okay? So let's say C is just some number again. I'm not fixing an interval beforehand now. So C is some number. Then if there is an open interval, if I can find an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. Okay. It is not necessarily an absolute maximum. If you fix an interval beforehand, this f of C might not be an absolute maximum. But there's a smaller interval where f of c is an absolute maximum. So, for instance, the difference between relative extrema and absolute extrema. So here's a function where I have my interval is a to b, okay? So this function has an absolute maximum at this endpoint, at b. But it has a relative maximum here. And the reason is, if I take this smaller interval from, well, it's got to be open, actually. If I take this smaller interval from, say, that was a, b, let's say this is, I don't know, a tilde, b tilde. If I take this smaller interval and only focus on the function there, well, then it is an absolute maximum, okay, when you zoom in on that interval. So that's the difference between relative maximums and really relative minimums as well, and absolute maximums. Is a relative maximum just means I can find an interval where when I zoom in, it becomes an absolute maximum. Absolute maximums, you fix your interval first, and then it is the maximum on that interval. Okay. So, questions about relative maximums? Yes, that point there has a 0 value for the slope, right? And that's not, again, by accident. We'll come to that in a second. Okay, so in the same way, if there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum. Okay, of f. So, relative minimums and relative maximums can be absolute minimums and absolute maximums. It just depends on the function. They're not, just because one is relative doesn't mean it's not absolute. It just depends. But it also doesn't have to be the case, as with this graph that I drew at the top, it doesn't have to be the case that a relative maximum or relative minimum is the absolute maximum or absolute minimum on an interval. Okay, so the relative maxima is the plural of maximum, and relative minima occur at very special x values called critical numbers. Okay, critical numbers. That's an important phrase. So let's define critical numbers. Let f of x be defined at the number c. So f of c has to exist. Okay, that's important. A lot of people forget that when finding critical numbers. If f prime of c equals 0, so the tangent line of f at c is horizontal, or if f prime of c does not exist, then c is a critical number of f. Okay. Why do we care? Critical numbers are the only interior points where a function can have extreme values. Okay. So that's what this theorem here says. This theorem says that the only place that relative maxes or relative mins can happen are at these critical numbers. Specifically, it says if f has a relative maximum or a relative minimum at x equals c, then c is a critical number of f. Okay. I'm going to skip the proof so that I have a little more time to fill in some of these guys. So we're going to close with these guidelines on finding extreme values on a closed interval. Okay. So to find the extreme values of a continuous function, it's got to be continuous, on a closed interval, it's got to be closed. Closed interval a to b. Use these steps. find the blank blank of f in the open interval a, b. By the way, one thing I want to say, the extreme value theorem, if the interval is open, that doesn't necessarily mean that f doesn't have extreme values on that interval. We're just not guaranteed the existence of extreme values, okay? So I want to make that distinction. Okay, so step number 1, we're going to find the critical numbers of f in that open interval inside the closed interval a to b. Okay. Then step 2, we're going to evaluate f at each critical number. In the open interval a, b. Step 3, evaluate f at each. So this gives me the critical numbers. What's the only other place that my extreme values can occur? Yep, and where else? Let's think back to, well, I don't want to go all the way back. Let's think back to that first example I did. Did those extreme values occur at, yeah. Exactly, we want to evaluate f at each endpoint. Of the closed interval a to b. So you're going to get a big table of values, okay? You're going to get a big list of function values. Once you have that, you pick the smallest, that's the absolute minimum. And then you pick the biggest, and that's the absolute maximum. Okay? Any questions on this? All right. So, example. Does the extreme value theorem apply to the function f of x equals 1 over x on the closed interval -1 to 2? If it does, find the extreme values. If not, explain why. So really what I'm asking is, can I guarantee the existence of an absolute maximum and an absolute minimum for this function on this interval? What did the extreme value theorem require? It actually didn't require f to be differentiable. It was actually a little weaker than that even. It definitely needed, we definitely needed it on a closed interval. That's true. I agree with that. Oops. What else did we require? So that was the interval. What did we require for the function?
It has to be continuous.
Perfect. It has to be continuous. Is f of x equals 1 over x continuous on this interval? Well, we can graph it really quick, right? Desmos. 1 over x. Does that look like a continuous function? Can you draw that without picking up your pencil? Between minus, we want -2 or -1 to 2, right? So there's -1, there's 2. Does that look continuous? No, this is not continuous because we can't divide by 0, right? The fact that, let me go back here now. The fact that 0 is in that closed interval tells me that the extreme value theorem does not apply. F of x is not continuous at 0. So we cannot apply the extreme value theorem. Okay. Now, does that mean that this function doesn't have an absolute maximum or absolute minimum on this interval? No, that's not what that means. it actually does have an absolute, no, it doesn't. It doesn't have either of those. But we can't say that for sure just because we can't apply the extreme value theorem. Okay? All we can say is we are not guaranteed the existence of absolute maxes or absolute mins for this function. Okay, we'll pick up from here tomorrow, and we'll find some extreme values for some functions. Okay. Thank you all for being here. Make sure if you have any questions, email me or come into office hours.
Thank you.
Thank you.